For example number 3, we're asked to graph and to analyze the following equation. We need to write it into standard form, so we're going to rewrite it so we have 4x squared minus 16x minus y squared minus 2y is equal to negative 11. Before we can do completing the square, we need to make sure we don't have any coefficients beside 1 in front of our square terms. So we're going to GCF the 4. So we're going to get x squared minus 4x. We're going to GCF the negative, so we're going to get positive y squared, positive 2y, still equaling to negative 11. When we do our completing the square, we're going to get half of this coefficient, which is 2, and we're going to square it, and we're going to add that here. We're going to do the same thing over here. We're going to get half of 2, which is 1, and we're going to square it, and we're going to add it right here. Now remember that when we're done and we do the distributive property with the 4 with this parentheses, we should get 4x squared, negative 16x, and when I multiply 4 times 4, I get 16. And that's what we need to add to the other side. We do the same thing for the y's. If I distribute the negative into this parentheses, I get negative y squared minus 2y and then minus 1. So I got to subtract 1 to both sides. From here, we can rewrite our problem into 4x minus 2 squared, that's the factored form of this parentheses, minus y plus 1 squared, that's the factored form of this parentheses, and we add up all of these integers here, and we're going to find that that is a positive 4. From here, we need to have our equation equal to 1, so we're going to divide by 4 to both sides. We're going to have x minus 2 squared minus y plus 1 squared over 4 is equal to 1. So that it looks more like what we're familiar with as a standard form of a hyperbola, I went on ahead and put that over 1 so we can have our a squared here. Now we're ready to start graphing. Before we do that, let's get our information that our center is located at 2, negative 1, that our little a is equal to 1 because it's listed first, little b is equal to 2, and little c is related to a and b by c squared is equal to a squared plus b squared. So c squared is equal to 1 plus 4, which is 5. So little c is the square root of 5. Since we're graphing, we can approximate that to 2.2. I think we're ready to start graphing. Let's bring in some graph paper. We're going to start graphing with our center, which is at 2, negative 1. We're going to go a, which is 1, in the horizontal direction because that's located under the x. So over 1 and over 1. Remember, those are our vertices, so I'm going to go ahead and put V's for these guys to remind me of that. We're going to go 2 in the up and down direction from our center up to down 2. And really what we're looking for is our rectangle, so we're going to go find our corners of our rectangle. And then while I'm here, let's find a slope from the center to the upper right box. So let's go up 1, 2, and over 1. So our slope is up 2 over 1. We're going to use that for our asymptotes. So let's draw asymptotes. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So we can see where our asymptote is going to be. And since we want it dashed, we can see that already happening here. We'll do the other asymptote similarly. So there's our asymptotes. Let's go find our focus. Remember, our focus is 2.2 away in the same direction as our vertices. So I'm going to go 1, 2.2, 1, 2 and a little bit. Those are our focus. From our focus, we're going to find our lattice rectum, which is 2b squared over a. So 2b squared is 4, a is 1, so we get 8. So we're going to find, we need to go half from our focus. We're going to go up 1, 2, 3, 4. Notice it's really close to my asymptote. 1, 2, 3, 4. Do the same thing with this focus. Go down 1, 2, 3, 4. And go up 1, 2, 3, 4. So we're ready to graph hyperbola by going to the vertex, which is this dot, towards our lattice rectum point, towards our asymptote. From our vertex, towards our lattice rectum, towards our asymptotes. So vertex, around the focus, to my lattice rectum point, and then towards my asymptotes. So those green lines represent our hyperbola. Last thing we need to do is to make sure we state our asymptotes. So our equation is going to be y minus a negative 1, which would be y plus 1, is equal to plus or minus our slope, which is 2, or 2 over 1, and our x value of x minus 2. Again, we can also state the points of our vertices. Remember, we started at the center and we went left and right, so it's going to be 2 plus or minus a, which is 1, comma negative 1. So we're going to find our points to be at 3 comma negative 1 and another one at 1 comma negative 1. And we can do that similarly for the foci. We would do 2 plus or minus the square root of 5 comma negative 1, and we can write those out separately. That should be the end of example number 3. Let's go to example number 4. The nuclear power plant problem. We're not going to spend too much time on this one. I just want to make sure that we can still understand what's going on in terms of hyperbolas. Let me first see if I can show you a picture of what a nuclear plant tower, cooling tower, looks like. So I googled nuclear power plant towers, and these are the cooling towers that we're talking about, and we can clearly see this one right here as a good hyperboloid. So let's go back to our example. So it says some nuclear power plants utilize the natural draft cooling towers in the shape of a hyperboloid, a solid obtained by rotating a hyperbola about its conjugate axis. Suppose that such a cooling tower has a base of 400 feet and the diameter at its narrowest point, which is 360 feet above the ground, is 200 feet. If the diameter of the top of the tower is given, our job is to find out how tall is the tower. So we're going to start by drawing a representation of this. We're going to say that we have a hyperboloid doing something like this. What we do know that down here on the ground, from one end to the other end, down here the diameter is 400 feet. And we also know that at the narrowest point, that's at 200 feet. And we know that that happens 360 feet in the air. So we also are given that at the top, that this one is 300 feet in diameter, not the 400 down here at the bottom. So let's come up with a coordinate system. So one of the best things that we're going to find is, let's make sure we have it going down this way so that we can see our hyperbola going horizontally. So let's put our x-axis here, our y-axis up here, and we can see that we're going to have our center at 0, 0. We'll also know that we're going to have our equation to be horizontally is going to be x minus h squared over a squared minus y minus k squared over b squared is equal to 1. So that's our equation we're going to use because we're going to have a hyperbola that is in this direction in terms of horizontal. So let's come up with our center we said was 0, so this is going to become x squared minus y squared is equal to 1. So now we need to figure out a squared and b squared. Well, if this is our vertex here, we know this distance is 100, so a is 100, so a squared is 100 squared. So we need to go figure out b squared. Well, if I knew a point, x and y, then I can plug it into this equation, and the only thing we would be looking for is b squared. So we do know a point. We know this point down here. We know that if we come over this much in terms of x, that value is 200 because of the diameter at the bottom, half of that. So we come over 200. That's going to be our x value. And our y value is going down to this point, which is negative 360 feet. So we're going to plug in x is equal to 200. We're going to plug in y is equal to a negative 360 feet. I'm going to plug those in. Don't forget you're going to square them so that you can plug it into your equation. And once you do that, you're going to find that b squared is equal to 43,200, which means that if we want to write our equation, we're going to find our equation to be x squared over 100 squared minus y squared over 43,200, because that's b squared. Now that we have our equation, we can find out what our height is. What we do know is that our x value would be 150. That's going to be our radius of the top. So we would let x equal to 150 feet in our equation, and then we would solve for y. And that will give me the height of my tower. So I'm going to stop it right here. This concludes this video.